So we need to define and be familiar with the terminology. Borrow pit is the area that you bring the soil material and you dump the soil at a given location and spread it. So then if you spread it, it's gonna be in the loose state because it's not been compacted yet. And then you compact it. Okay? And when you compact it, each layer for one dump is called a lift. So for example, this is spreaded, and the spreaded initial thickness will be like 30 centimeter or 20 centimeter. Right? This will be reduced when you compact it. So then the lift thickness is called the compacted layer thickness. So the borrow pit is could be anywhere. It could be near the lake or near the river or some just open area. The area where the material has been dumped to another location. And usually compaction done in layers, and it's called a lift. And the spread of material in layers 6 to 18 inches, 16 to 45 centimeters per lift. And then compact with the roller, then control the dry density and the water content for each layer. So when you dump the soil and spread it, it's already mixed with water, right? So before that, you have to determine how much water to be added or how much water to be removed. So when you compact with the roller or some equipment, we have to determine how many passes are we going to go over. So one lift, the roller can go 1 time, 2 times, 3 times, 4 times, or as many as you want, right? So that's called the number of passes. And also what type of equipment are you going to use? So we can use really heavy drum roller or small or medium size, the size of the roller or weight of the roller. And also when you pull the roller, you can go over at a really fast speed or slow speed. So it's called the speed of the roller. So these speed needs to be determined for the field compaction practice. 현장에서 저거를 정해야 된다는 거죠. So here, objective, how much thickness are you going to use for the each field? How many passes? How fast do we tow? And what roller do we use? Like how heavy the roller should be. And before that, we will determine the water content. So then what do we do? So once the compaction is done with the roller for each lift, then we check whether the dry density is greater than what we expected or we designed. So you have a design dry density, and the field dry density should be greater than that. Right? So that's what we want to talk about. 그러니까 field compaction test에서 끝나고 나면 여기에 얼마나 잘 다졌는지를 검사를 꼭 해야 됩니다. 그게 이제 quality control control이요. Okay, so we'll see what type of a variety of the field compaction equipment. The first one is a smooth wheel roller. 이게 가장 많이 보이는 건데, but we don't use it for the soil. This one is generally used for the asphalt pavement. Smooth and 100% coverage means that the whole area of this, whole length is used to compact the material of it. And it's this static weight. It doesn't have vibrator or it doesn't have the protrusion. The pneumatic roller is also used for the asphalt pavement, and these are the tires, and tire applies the pressure to the aggregate layers. So it can be used for the highway fields and earthing construction. And Sheepsfoot rollers, it has some protrusion, like a pokey metal. 여기에 중간중간에 눌러주는 게 있죠. So it's called the protrusions or rectangular shaped protrusion or the pits, and it gives the higher contact pressure comparing to the static drum, like a smooth drums. The pressure 훨씬 더 크겠죠, 이 눌러줄 때. So this is commonly used for the clay type of soil, fine grained soil. So it's best suited for clay soil. And the compacted effort is static weight plus kneading. And tamping foot roller, it also has some protrusions, and it's best for the compacting fine grained soil and static weight, and then another type of the sheepsfoot rollers. And it compacts from the base of the layer to the top of the layer and walks out when the lift is compacted and used with the fine grained soil. Foot is normally round or rectangular, so the shape of this foot can be rectangular or round. And the other is the smooth wheel with the vibrating drum. So it applies the vibration with the motor. And that's good for the granular soil. So we've seen the video that when you apply the vibration, that it settles down, right? With the compaction with that. So vertical vibration, and it's static weight plus vibration, and it's suitable for the granular soil. And this is dynamic compaction. Some of you may have seen this one.
Crawler cranes are often used for dynamic compaction of loose gravel or sand. The Liebherr HS895, seen here during final testing prior to delivery, is equipped with an automated system to ensure max.
So you have temper for the dead weight and bring it to a certain height and then drop it. You see? And this is for the dynamic compaction. So this is for the deep depth. So for commonly the compactor with a drum, the effective depth of the compaction is about maybe like 15 centimeter, 50 centimeter, like half meter, less than half meter. So you have to have a layer by layer. So maybe like spread like 30 centimeter and compacted, and then another 30 centimeter and compacted. No? That's what you done for the common practice. But when your ground is very loose, so that you want to compact like for a certain depth. For example, you have a very weak layer, 5 meter deep from the ground, and you want to compact this very weak sand layer. Then you're going to use this kind of a technique, the deep dynamic compaction technique. And this can be effective in 10 to 15 meters up to. So it can compact up to like 15 meter deep. So, of course, you have to design the how much weight you're gonna use and how high you're gonna bring it up, and then how many times are you gonna drop it. For this deep dynamic compaction, the other course for the site and soil improvement class at the senior level will cover it. 다른 과목에서 간단하게 드립니다. So dynamic compaction can achieve densification to a depth of about 30 feet, so 10 meters. So summary is when we do the standard compaction test, we apply the impact. So we bring the hammer and then drop it. It's called the impact. And the fine grained soil, we need the kneading effect with a higher contact pressure. So you see there are very small protrusions that apply the higher pressure. And for the granular soil or coarse grained soil, vibration is very effective. And static not very efficient, but you can use it for the very shallow depths or the asphalt pavement. So this is another summary of that, shows in there each compactor characteristic and the type of compaction and the applicable soils. So as you can see, for the clay, as the clay fraction becomes higher, then you will need the tamping or Sheepsfoot. But as the sand and gravel becomes more, then vibration is detected. So the decision on equipment, like mass and size, and if you want the vibration, then the vibrating frequency, and what else? The initial density, tensor distribution, and the water content, and then construction procedure, number of passes, and lift thickness, and the frequency of the operation vibrator, and the towing speed. So we can easily think the heavier is better, right? Even though it may cost more expensive. What else? Lift thickness, thinner will be better. And towing speed, slower will be better. But you can see that it's going to increase the time of the construction. So also the labor cost will increase. So we'll have to optimize that to minimize the cost. So look at this chart. It shows the effective frequency range for the compaction. So let's look at this gravel, sand, clay, or well-graded sand. And you can see the vibration around like 2000 CPM cycle per minute. So it's a 분당 회전수죠. Cycle around RPM or cycle per minute. 2000 cycle per minute is about like optimum. And for the clay soil, it's a little bit different depending on the type of clay. So heavy clay is here, and the clay soil is here. But generally, the people use this grading around 2000 to like 2500. And travel speed or towing speed. And as the towing speed decreases, so it becomes more slower. So here, 2¼ like 1.5 miles per hour, and 3/4. And as you tow slowly, the dry density increases, right? Dry density increases first, faster, and also we can see that as the roller coverage increases, it means that so 4 means that the number of passes are 4 times. You're going over back and forth, so that gives you the 4 times number of passes. So as the number of passes increases, the dry density increases. Right? But for some soil, it's not effective over 8 times. So when the number of passes exceeds the 8, and it doesn't increase the dry density anymore. So there should be some optimum number that you can choose. And lower passes. So another one for the number of passes. When you apply the 2 passes, then density distribution is like this. And what is it? 5 roller density distribution, and 15 and 45. And you can see there are quite significant increase from less than, this is 103, and now it's 107. But after 5 passes, then still it's 107, and also 107, maybe 108. So you can see maybe like 5 is the maximum number, or the optimum number you can apply. So this kind of control is done before you determine the design. So then, So this is from the one lip thickness. So here 3 feet is about what? How much is it? 3 feet. It's about 1 meter. 3 feet is 1 meter, right? So if we, for example, let's say that our criteria, the minimum dry density that we can achieve, that we need to achieve, is this. Oh, this is 105. So then this thickness can be this much thick. So that's about 2 feet, 2.5 feet, 70 centimeters. So it will be depending on what's the minimum dry density you need to achieve. If the minimum dry density increases, then the lip thickness should be thinner, right? So that's how we determine the lip height. So when you have this kind of a compaction dry density curve over the depth, then determine the minimum allowable relative density or dry density, and then just overlap the curve and see what's the thickness that can achieve the minimum dry density or minimum relative density. So, yeah, and more example, we want to do later. Then specification and the compaction control. So there are design and construction procedures. Let me read this one. Laboratory tests are conducted on samples of proposed bottle material to define the properties and required for design, maximum dry density, and the optimal water content. So this is like a standard proper test or the modified proper test that you perform in the lab. And after the all structure is designed, the compaction specifications are written. So, like for example, dam, if it's the dam, then you know what's the dry density to be achieved. And field compaction procedure or the specifications are written, and the control tests are specified. The result of this becomes the standard for the controlling the project. So there are two types of the compaction control. One is the method specifications. And here, if Tae-Hyuk is the boss of the compaction company, and he has the engineer at the and Dong-Hwan is working in the 농업청공사. 그래서 일한다고 합시다. From local government, and the local government wants to build the embankment, and then you can ask Tae-Hyuk buy this kind of equipment and 5 times number of passes, and what else? Swing speed 4 km per hour, lip thickness 15 centimeters. You define everything and give them a specification, and then Tae-Hyuk and Yoon do just to do as you are told. And it's called the method specification. So height and weight and number of passes as well as the lip thickness are specified. So then here Tae-Hyuk and Dong-Hwan will be responsible for the result because you done what you were told to, right? So it's the owner responsible method, and typically used for a large compaction project. So in that case, if the Dong-Hwan is just the like official in the local government, then you hire the design company, the engineering company to specify the procedure. So, and then you two have a separate contract, and then you two have a separate contract. And the second one is called the end product specification. So in this case, owner doesn't care about how you achieve the dry density. So let's say the maximum dry density is 100, and Dong-Hwan specified it, the minimum allowable density is 97% of that maximum dry density. So then, Uyeon and Tae-Hyuk will discuss how to achieve that goal. And then also at the same time, you will think about how to decrease the cost, right? So you are responsible for the result in that case. And then Dong-won will inspect the dry density when it's done. And when it's all okay, then he will pay the money. Okay? So that's called the end product specification. So this specification is used for most highways and building foundation. And the contractor is able to obtain the specified relative compaction. And they care the results only. And they don't care what equipment you have used, how much water content you have used, and they don't care. Open specified, well, sometimes the water content is important also, they may care. Open specified as percent of the maximum dry density of the standard photo test, like 95% of the standard photo test. It means that the 95 minimum is the 95% of the maximum dry density from the standard photo test. And sometimes we'll provide a range of the water content too. So you have to use like plus minus 2% or plus minus 3% or plus minus 1%, or you have to compact it in the dry side of the optimum or the wet side of the optimum, depending on the structure. What did I say? For the dam structure, it's good to be compacted on west side of the optimum. So then owner may specify the water content range. From water optimum plus 2% or something like that. So he will give their range. And contractor responsible for achieving the dry density, owner is fixed for density. Contractor will use the slightly higher compactive effort to achieve the requirement to pass the inspection. So then for inspection or compaction control, they use this term, relative compaction or percent compaction. We widely use the relative compaction, RC, and RC is defined as the field dry density over laboratory obtained maximum dry density times 100. And typically, the project requires 90 to 95% or sometimes 97%. And then how to determine the water content? So these are the compaction curve, A and B, obtained from the lab with different compactive effort. Maybe C using the standard process test, and A from the modified process test, because the modified process has a higher compactive effort. Maybe B with the mediocre or medium compactive effort. So then, the owner will tell you what's the level of the compactive effort using the field equipment. For example, we are using the vibratory smooth wheel drum, then that has a certain amount of compactive effort. So then that will be, let's say that's comparable to A. Yeah, that's comparable to A. So then, so we'll use this A curve because the compactive efforts are similar to each other with the lab and with the field. So then, owner asks for 90% of the relative compaction. So then, this is the maximum. Say that maximum dry density of like 1800, and 0.9, if you multiply that, like 18 times 9, so somewhere here. And then this is the water content range that you have to use to achieve the that kind of relative compaction. 9%, and yeah. So the amount of water that you should add will be between X to Y. If the water content is beyond this range, then it will be very hard to achieve that dry density. So compact effort that can be obtained by the specific compaction equipment, and if the placement water is outside the range, then it's difficult to achieve the relative compaction, no matter how much the contractor compacted. Thus, it is necessary at times to wet or dry soil prior to rolling in the field. And I like this curve, and it's very, it gives you very many ideas about the soil. Here, the maximum dry density. So this is from the standard of the test, and you can see the soil A, soil 1, has the maximum dry density among these 8 types of soil. Okay? And 1 is what? Well-graded silt, or well-graded sand with silt, some silt. So with silt means that it's a DO symbol, so the fine fraction is, how much is the fine fraction? 5 to 12%. So it's not that much, but it's very helpful for the compaction. And then the next one is the well-graded silt. And so this second one. And what's the poorest one? The fat clay, CH, is the clay with the high plasticity. And 7, so 7 is here. And 6 is the ML, the silt, is around here. And what else here? Silty clay is around 5. Right. So this means that as you have more fines or more clays, optimum water content, how does it behave? You need higher water content. The optimum water content increases with the clay fraction, right? And also, what happens to the dry density? As you add more clay, the maximum dry density increase or decrease? Decreases. Huh? So this is kind of good lesson to take. And the maximum dry density is around like 2 megagram per cubic meter. So it's like 2,000 kilogram per cubic meter. And the lower range for the fine grained soil is around like 1,600 to 1,700 kilogram per cubic meter in terms of the dry density. For the fat clay, the pure water content is over 20%. It can be over 20%. So also that's interesting. 질문 있나요? 질문 있는 것 같은데. 아니. You can stop me anytime. Okay. And then this is kind of a US like textbook. So we do have a different design criteria, but imagine that you're building 2 kilometer embankment, 2 kilometer long embankment. How often do you have to inspect the dry density after the compaction? 얼마나 자주 해야 될까요? 그러니까 만약에 2km 짓는다. 그러면 이제 얘네들이 컴팩션 하잖아요. 컴팩션 하고 나서 다 했습니다 할 때 do we need just one sample for whole 2 kilometer or like every 1 meter? Then we'll need 2,000 samples, right? Specimen. So that's the another criteria we have to determine. So here they said they are every 1,000 to 3,000 cubic meter, you can do a field test. Or maybe, I'm not sure about in Korea, but you can do it like every 50 meter, or every 20 meter, depending on the importance of the structure. 그런 식으로 하시겠죠. Or you can require more because you're the owner and you're responsible as a government person. And if there's some curved structure that's vulnerable for some kind of failure, mechanical failure, then you can require more inspection around the that specific critical zone. 좀 약간 여기는 조금 위험할 것 같은 그런 지역이 있다. 그러면은 여기만 좀 더 해주세요 할 수도 있는 거죠. So it's not specified. It's not, but it can flexible depending on the type of structure and the type of geology. but it's also important part to determine how often do we do the compaction control. So then for the fuel control test, what do we measure? We are measuring dry density and water content, right? So then how do we measure the water content and dry density from the field? Water content is easy. You can just take the sample, the wet sample, measure the total mass, and oven dry it and measure the dry mass, right? So, but for the dry density, we have to think carefully. You can try it, and then you can measure the mass. So then you get the dry mass. But we need to measure the volume to get the dry density, right? So these are the methods to measure the volume of that soil. So before you read this one, you can imagine how would you like to measure the volume of excavated zone. So let's say here, this is the ground. I want to excavate with the shovel a little bit, so making like 40 centimeter, and maybe like 10 centimeter. You're digging, and it's not gonna be like really flat. So I want to measure the volume exactly. Okay, 이거 안 보이네. 안 보이죠? 그냥 하고 난 다음에 한 곳에 볼륨을 재야 돼요. 그죠? 사람들이 온갖 아이디어를 다 했어. 쉬운 방법부터 very easy and straightforward method to the very complex method. There are many attempts so far. Celine, how would you measure the volume? It's okay. Any idea? 방수팩 같은 거 깔고 물을 붓는데 포를 리퀴드 비슷한 거를 한 게 두 번째 방법이에요. 그죠? 예, 세 번째 방법. So you can place a very thin and flexible sheet at the excavated dug, the pit hole, and then pour the oil or the water and measure the volume of it. 뭐 이것도 쉬운 건 아니에요. 왜냐면 it's not very easy because there could be always like a gap. 갭이 얼마든지 있을 수 있고. You don't want to have like a stiff material, so no. If it's flexible, it will be better. And the other method they tried is to use the balloon and use the air pressure to fit inside the wall of the soil and see the volume of that balloon. And the first one, this one is the commonly used one, and they do have a kind of a which you may call it. 이거 모래시계를 뭐라고 그러니? Like a sand at the top, and then just pour the sand and see how much sand goes down from the jar. So it's like using a water, using a sand instead of the water to fill inside the volume. And I've seen this one a lot in States and in Korea. 이걸 제일 많이 쓰는 것 같아요. Still, the sand can be compacted in different ways. So there could be some error issues. So the measuring error is mainly from determination of the volume of the excavated material. For the sand cone, the vibration from nearby working equipment can increase the density of the sand in the hole, which will give a larger hole volume and a lower fuel density. So when you pour the sand, it's loosely deposited from the job, right? And if there's a vibration walking around with the heavy equipment, then it can be compacted just by the vibration. So then the sand, you need more sand to fill the hole than the usual. So then the volume will be largely estimated. If the compacted fill is gravel or contains a large gravel particle, then any kind of unevenness in the wall of the hole causes significant error in the balloon method. If the soil is coarse sand or gravel, none of the liquid method works well unless the hole is very large, and the polyethylene sheet is used to contain the water or oil. So then there are non-destructive methods. So that was the destructive method. And this is a non-destructive method. People use the nuclear densometer or nuclear density meter, and it's very fast. It just reads directly, and it's useful to make the corrective action repetitive measurement as possible. But disadvantage is the equipment itself is high, expensive, and because you use the nuclear source, you need some training before you use it. And from nuclear densometer, there are direct transmission, backscatter, air gap type, but you can read it through. But generally, from the source, it emits the gamma ray, and the detector captures how much gamma rays are received. So if the materials are dense, then there are more scattering, so that you get the less flux. But if the material is loose, then the scattering is less, so that the flux is high. So you get the more radiation. So using that principle, this calculate and estimate the dry density. And also the water content is too. So if there's more water, then the water hydrogen atom absorbs the radiation, so that you get less wave or the gamma rays. Okay.